Start recording. Okie dokie. So where we left off, we'd taken this Murmur hash 3, and we just copy pasted it, and we were going through it, basically line by line, porting it to C# and sort of discussing what everything's doing. We brought in our value 128 from the River City code base, and we've got the rotate left 64 because we can't issue that instruction, sadly. And we can't aggressive inline, also sadly. But, that's fine, these things happen. Not a huge deal, it's not that slow. Like, it's a few extra instructions, but we can deal with that. So, in the sort of original body of this method, what the old code was doing, and I just realized I've started this without having the source code to reference here. But in the original code, what it was doing was it was just taking, well, it was calling something called getBlock64. And getBlock64, to get a 64-bit block, and find it, is just, it's doing an array index, array lookup. So it's dealing with read alignment here. So we're gonna have a quick discussion about what that means, because I think it will come in sort of handy shortly. I have looked into the future, and so what we have is we've got here's a K1 and K2, and both of these are 64 bits. And so what we were doing is we've got our string, and each of those 64 bits divides up into 16-bit characters. So we've got 4 characters of 16 bits, each getting copied in. And last time we did the correct manipulations here to make that happen. My window's around. Alright, so in the C++ version, what they've got, they're going through this get block method, which I guess is just so you can quickly replace that and fix it everywhere. So they've got K1 and K2, and they're just treating this as an arbitrary pointer, so byte star. So it's just like, just give me the start of that, and so it's effectively bytes. But rather than copying it byte by byte, they don't go like we went copy that in, copy that in, copy that, and so on. They're just taking the whole thing and copying it all at once, because they can just treat this byte star. They can just cast it to a 64-bit pointer and do that. So that should all be fairly familiar at this point, yes?
Yep.
Okay, so we can't do that with our string in C#. We can do it if we were to cast the string, like we can do fixed star s equals key, and we can then stick it in an unsafe fixed block, take the pointer, and then cast the pointer to a 64-bit pointer and do exactly what they were doing. We could do that. However, we can't do that with a string builder, because the string builder's got its own internal format. I believe it uses what's called a rope, which is basically, it's not a single buffer, it's actually multiple buffers, like it's a list of buffers. Which means you can't take the pointer to like just the buffer that it's using.
Right.
Not to mention that it's also probably an issue, like for the same reason you can't take a pointer to, like, let's bring that back, like a well, this is bad code, but let's say a list of character. You can't get the pointer to the internal buffer of this, and the reason for that is at some point, even though this is sort of a sensible operation, like you could get a pointer to the buffer, the buffer could expand at some point. And you remember we talked about that when we were doing manual buffer handling with our own arrays. It's like you double the size of the array by calling array.resize, and that basically reallocates the array somewhere else with a different size, and it copies the content in. So suddenly our pointer becomes invalid and may get collected. So we can't do a string builder, so there's not really that much point in doing it with string. It's probably, in the long run, better to just have the code for string builder and string the same. And if for whatever reason it's like a tiny bit slower, hopefully we're not calling this so often that it matters. And if it does start to matter, then maybe we can worry about it then, possibly even make this a native function. Because the other problem that we have if we do the thing with fixed, is this is going to pin key, which is probably fine here because we're actually not allocating particularly frequently or anything. And so the chances that we'll collect inside this fixed block and stick a dirty great hole in the middle of our heap is quite low. However, it's something that needs to be thought about.
Can you explain pinning a little more?
Okay.
Just for
yeah. So where is my thing? So let's say we have a let's just say we've got a heap and it's got some objects in it of arbitrary size, maybe it's got some small ones and a big one. And let's say we go ahead and like delete these objects, and then we no longer reference these objects. So the GC comes along and it will do a compaction. So we end up with that object, we end up with that object, and then we end up with that object. And they just sort of come down like that one gets copied into the new heap, that one gets copied, and that one gets copied. So this is called, this is a compaction phase.
Right.
And this is obviously mark phase. Is we've marked those as not being reachable. However, if say we were to pin this sucker, what this tells the GC is it can't do this. It can't compact it. It actually has to leave it there.
And pinning happens inside the fixed block because it doesn't want the pointer to change if we resize?
Exactly. So the pointer that we got, so word star foo points to here when we call fixed. So and then when we're done, we want it to still point there. So and then what happens is the garbage collector now gets, I actually haven't measured this, but certainly they say don't do it because it's quite slow. That one comes down, that's fine. Then it's like, oh, we can't move that, we have to leave that. But then we have to go ahead and bring this one in, which means this one compacts down to here. and then let's say we have another object off the side here, or we allocate another one. Now it's got to be like, oh, it's not going to fit here, so we have to like, oh, we'll stick it there. And so drawing the arrows correctly, so that one like comes down fixed, and this one like has to go there, and then this is our new allocation or whatever.
Now why go through that? Why not just leave the entire section blank and go back, like pretend that you're compacted? Like, is that the coherency thing where everything needs to be close together for access?
Yes, it's because okay, so it's partly coherency. It's like, all right, let's just keep the objects together. What this is glossed over is the fact that this is actually a generational process. So you can implement a garbage collector like this, where it like compacts into the same space, because it's like compacting to the same block of memory. What actually happens is slightly different. So you've got now it's really stretching my memory of how this works, because I read about it once and forgot half the details, but you've got generation 0, and then gen 1 and gen 2. Let's just say they're about the same. Let's separate out gen 2 just for now, I'm not sure how useful that will be. And then we also have the large object heap, which is handled differently. I think from memory, it's never compacts. So
right.
And I think it's objects greater than 8 kilobytes. So if you ever make an object that's greater than 8 kilobytes, it's going to go into the large object heap. And so the problem there is they're basically, because it never compacts and it's a single heap, every object gets treated effectively like it's pinned as far as compaction goes. So it's
right.
Can fragment. So you can see, that should say blank. So you've got this blank space here that's too small to be useful. And so you can imagine what happens is if you like allocate in like a random order and like deallocate as well, sort of in a fairly hodgepodge random way, you can end up with lots and lots of little holes and slowly run out of memory because you've filled it with these unusable blank spaces.
That's essentially fragmentation, right? That's the whole...
Yes, so that's fragmentation. Now, getting back to the actual garbage collected heap, that's sort of compacting garbage collected heap. So Gen 0 is per thread, and now if anyone's watching this for some reason and wants to actually know like a reference that's absolutely correct, go and read the book of the runtime. Book of the runtime. That will actually explain this in a lot more detail. So it's per thread. It's extremely fast to allocate from, because you don't even have to stop and talk to any other threads and like be like, oh guys, you know, I'm locking because I'm like allocating something from the large object heap, for example.
Right.
So it's basically, to do this, it increments a pointer. It's like it takes, it's like so here's, I'll keep coloring it yellow because I need it. So previously the new position was here, and then I allocated this thing, and so it moved to there. So it's like increment by, you know, n bytes, however long this thing allocating is, and return that. So it's effectively the operation PTR, return pointer plus equals, no, actually no, it's I was going to say it's plus plus as in post increment, but I mean it's assembly anyway. So yeah, it's I won't write out the code, but you get the idea. It increments it and returns the old value to you as your location to allocate that object in.
Right.
So it's per thread, and then every time you hit a garbage collection, if you're doing gen 0, now I've actually run into a point in my memory of this which is actually a bit fuzzy. I think there's actually 2 of these. And so when you do a gen 0 collection, you basically have the objects there and the objects there, and rather than compacting like into the same space, which like if nothing goes away or the first half of your data doesn't go away, it can just doesn't get copied, it just stays there. Because this is such a small amount of data and it's sort of generic, I believe what happens, and I could be wrong, but I'm pretty sure what happens is it like ping pongs. So it's like, all right, we've marked our objects, we're going to sweep them, and we're going to compact them, we're going to copy them here. So if there's like object, 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 they get compacted down to object, object, object. If that makes sense. In that copying process.
We've covered that in some detail before.
And then obviously it goes back the other way. In a Gen 0 collection. So it's quite fast because there's a small amount of data. There's something called a card table that handles it handles when you like write a pointer out. It's like, let's just mark which pointers have changed, so it knows where to check. So when it does a Gen 0, it doesn't have to look at everything in the other generations. It just looks at the card table for what's data has been modified. That's probably a little complicated to go into, and it doesn't really affect compacting. And then when you go to Gen 1, I believe it is just one block. It's not per thread. And when you compact it, it just goes out of whichever is the active one and sticks it on the end. See, this is where I'm a little confused. I'm like, at which point does it go here, and which point does it go here? Is it a Gen 0 collection or a Gen 1? I can't remember exactly.
It's probably not relevant.
Yeah. So this is not something you need to, like, unless you're doing garbage collection optimization at some point. But suffice to say, and then it goes into the generation 2 thing. And you can watch this happen if you have the what's it called, the .NET performance optimization-y thing. It's not Reflector. It's you know what I'm talking about though, right? The
like, isn't it Perfmon or no? It's not.
No, the name has escaped me, but it's Profiler, the .NET Profiler.
Oh, just the one that's built in the Studio.
There is a sort of version of it. It's not as good, but it is built into Visual Studio. You can do this, but it's called the .NET Profiler, I believe.
Or a CLR profiler.
Yeah, I think that might be right.
That's the standalone tool.
Yeah, and it's a profiler, but it's a memory profiler, and it will actually tell you which objects are where, when the collection's happening, and so on. You can actually get a fairly good sense of what's actually happening under the hood as far as this process goes. How big your heap is, how long it's taking to do various things, what's allocating memory, so on and so forth. What's going into the large object heap, which is useful if you've got huge objects. And yeah, so I think I now cannot remember why we started this digression. but suffice to say, when we were looking at this, we're talking about
well,
fixed.
I was asking why not just not compact when we run into a pinned piece, and then you explain fragmentation.
So basically, you have to well, you don't have to compact, but well, no, at some point you have to compact because that's how you free memory, basically. So you do actually want more memory at some point, because presumably if you're allocating memory, you cause a garbage collection. So conversely, if you've caused a garbage collection, you are allocating memory, and if you're allocating memory, you're probably allocating memory regularly, which means that you're going to need to allocate more memory in the future, which means you need to have some memory free. So
right.
If you've got like a fixed object here and it was pinned a while ago, all of a sudden the thing that's doing the compacting has to remember where all of those things are and check a table of where not to put stuff when it does this process.
Yeah, I guess I didn't mean like skipping compacting so much as like, I know if you skipped a block because you ran into a pinned piece of memory, I don't know why it wouldn't just mark that for later, and then when it started to have memory pressure, it could go find all the missing blocks. But that's just, I don't know, I don't have understanding of it enough, but to know why you need to continuously sort of proactively compact rather than just track where the holes are.
Well, I mean, it does track where the holes are, but basically once it's been asked to do a collection, because I mean the user might be like, I need you to collect, please, because it might call gc.collect. You have to do the collection, and so the only real option is to do the whole collection at whichever generation the user requests. And so the only thing you can do is just say, well, we'll just remember where those things are and not write into those spots. So there's not really any other option. Unless I'm misunderstanding your question.
No, that's good.
Yeah. So and so obviously, if you have a whole lot of fixed objects running around, you end up with these things that the garbage collector has to go off and read this table of pinned objects. And that slows the garbage collection process down, which is obviously already a slow process to begin with, so you don't want to make it slower. No one wants to install Apple updates. Okay, so so anyway, so we basically, that's the reasoning why we're not going to go off and implement this as a fixed thing just yet. The other thought is, if you're gonna fix a buffer and you want it to be fast, you may as well call out to a native assembly if you can. I guess if you're in a environment where you can ship a DLL. So if you're going to pin a buffer, you may as well also do a native call at that point. So you might implement this in C. So what am I after? Okay, so let's have a little look at the tail section. So this is what we're going to do next. And obviously this is doing something different. How would you describe what this is doing? So reading code is important, so tell me what you see.
Okay, well, the fact that it's a tail means we've run out of, I guess, full blocks, so it's dealing with whatever's left. Mm-hmm. And let's see. So we're allocating an array that's the size of the leftover pieces of data.
Well, just hold up a bit because you've stuck an array thing here when this was a pointer. So this is actually doing something slightly.
I did that because of the array accesses down here, and it was a lot of red. So I that must be a number. But
no, that's only because you don't have an unsafe block. Like.
Oh yeah.
But we're not going to do it unsafe, so we don't need to. But you could do this to make those go away.
Oh, cool.
Anyway, carry on.
We're allocating a buffer that holds the. Oh, hold on a second.
Yeah, I want to be very clear about what you're allocating or not allocating here.
Yeah. So, I'm not exactly sure what happened to data. What did that used to be called?
So data used to be, that's an excellent question. Let's look at the old code that we pulled out. Data is this thing here. So it is basically casting from a void star to a byte star.
Oh.
So it's just a pointer to our key. It is the key. It's the key. So yeah, you may as well write that.
Right. Okay, just give me a sec here.
Mm-hmm.
Well, that's interesting. I mean, this seems like quite a lot of data to be allocating. Our entire key, the length of our entire key, I guess. Plus the Go ahead. Sorry.
Well, I've added in a byte star here just to make it clear that this is this is what data was its key cast to a byte star, but yeah, don't necessarily add in anything there. Partly because this is like an exercise about reading what the code is doing.
Yeah. I guess.
Yeah. Try again.
I guess it's 4 bytes plus the number of blocks times 16.
Okay, I'm going to stop you here because there's a very important thing that I think you've said that's incorrect, and that is the word allocating. Because you'll see it's not allocating because you're not basically doing a new or anything with like an alloc or something in it.
No, you're right. It's actually just
so.
trying to find the end. That's what it's doing.
So yes.
Trying to find the pointer that represents the end of the string, or the end of the key. Yeah, it's just trying to find where we are in the array before we start looking at how, like, yeah. Sorry.
Yeah. So I just wanted to be super clear about that because yeah. Like if we've got
it kind of feels like it just wants to get whatever I is multiplied by the number of bits. But after we've done, if we were going to do it at the bottom of this, so it's just like, where's the end of it? Well, I guess that's literally where's the tail.
So we're just basically making a new pointer, or we're creating a pointer that is like, here's our, if this is the data in the blocks, like say it's
right.
So we've got okay, 1, 2, 1, 2, 1, and then 2, and it's partial. So this is so we're pointing to where we finished.
Right.
So that's what that does. So that's important to know because obviously we're going to have to do something with that. So let's move on to the rest of it.
Now, so we're sitting on the pointer where we're finished, and we have some amount of data on the other end, and we know that it's less than a full block.
Mm-hmm.
So it's less than, basically it's less than 16 bits, and
well, it's less than 128 bits.
Right. Sorry.
Yep.
Yeah, you're right. Sorry, it's 16. Yeah. The number of blocks is 16 times, or 8 times 2 because it's Unicode 16.
Yeah. So 16 bytes, 128 bits.
Right.
Yep.
Right. I should have said bytes. We know it's less than 16 bytes. And then len, I just got to remind myself. Len is, again, it's the length of the string. The length of the string, if it were 8 bits, times 2.
Yep. So length in bytes. Yep.
Right, and then we're masking it against the maximum. I know what this is trying to do. I'm not exactly concise about it, but basically it's trying to figure out. It's masking to figure out how many bytes are left.
Mm-hmm.
Exactly.
So
so we know where to start in this fall through.
This is something that I missed out when I was describing the other day. You recall the diagram that I had. Let's see if I can find it. On this one. So, we've got and is mask, or is combine, XOR is that, and so on, and then we've got the shifts. So there is one thing that I missed describing this, and let me quickly draw this out. New sheet. So if we've got, let's say, an 8-bit number, and we were to do shift right by 3. So basically we've got some number A B C D E F G H, and we are going to shift it down. It's going to be A B C D E. So a shift right by 3 is equivalent to a division by 8. It's equivalent to division by 8. So does that make sense so far?
Well, I mean, I don't want to do the math of that, but okay, sure.
So and you recall on the other diagram we had 2 to the n. So if n is
right.
if n is 3, then 2 times 2 times 2 is 8.
Right.
Sure. So you can tell how it's like you become fluent quite quickly in how to do that operation. But what I left out is this masking business. So it's like if we then were to say, and I'll do this in green, if our mask is 1 1 1 0 0 0 0 0, those are almost unreadable. Quite clear. All right, so if we do that, what we get down here when we do an AND operation, so we're doing AND 15, which is, I'll show you how to construct that in a second. We get FGH.
Huh?
So I'm working off.
You haven't shifted at 3. You just mean that? Yeah. Okay.
Yeah. So just ignore that one for the purpose of this particular bit of maths. So what this is basically remainder. And does it make a little bit of sense, sort of, how that works? So I've shifted off the bottom 3 bits here, and now I've masked off the bottom 3 bits here.
So
I've basically selected the bits that we didn't get in here.
Yeah, right. Okay.
So
as a whole, sure. Yeah.
So you can imagine if I were to try and reconstruct this, I could take this, I could multiply it by 8 or shift it left by 3, and then do an OR operation to OR in these ones, and I'd get back the original value. And so it is equivalent to division and kind of addition. But yeah, this is a remainder operation. So hopefully, like, the maths behind how remainders work is something you're sufficiently familiar with.
Yeah, other than the 15, like, okay. I know it's obviously 16 minus 1, but the minus 1 off by 1 being a famous thing.
Let me show you how we construct this, because this is quite a useful little technique. And so what they've done here is they haven't even written this out in full. Like, occasionally I would write this out in full, and occasionally you have to do it like Well, the number of bits that I shifted is not a constant. Like it's a constant 3 bits here, because we've done well, it's actually a little bit different. Have I made a mistake here? I don't think so. 16. Have I made a mistake? I don't think so. I think I may have made just a maths error. So this is multiplied by 16. This is 16. Maybe I just made a maths. Whoops! Come back. I think maybe I've just made a maths error, or something. Divide by 2, divide by 4, divide by 8. Oh, I've made a small maths error. The thing that I've drawn here doesn't match the thing in the thing. The thing that I've drawn is this. Does that make a little bit more sense now?
Yes.
Yeah.
Only because it's -1 from the amount that you divided, and we divided by 16, and we have 15 in the real world, and you divide by 8 and have 7.
It's like if it was 15, it would be that. It's like,
right.
It's just because I grabbed that example, and then grabbed the other thing for an example. So that's fine. So the way you construct this is actually kind of handy. So if you have to do like n, like a variable number of shift and then unshift, or shift and then grab a remainder, this is a useful technique. So what you do is you go, so you might do this, for example, if you were implementing like a bit buffer,
right,
where you have like, you've got some, you can put n bits of data in 1 byte, and then you have to grab whatever the remainder is and stick it in another byte or something, because you ran out of space.
Like in River City, the serializer packed booleans, so you probably did something like this for that, right? Figure out how many boolean slots you had left in your.
I guess so. I think there was some of this is a slightly different, but sort of it's the same concept. Like certainly you could build up that stuff from these concepts. Like all you need to know is this, and then I think you can build that same thing.
Okay.
So what you do is like, all right, I'm going to take 1. Let's do this in a different color so it's more visible. I take 1. 0, 0, 0, 0, 0, 0, 0. And then what I'm going to do is I'm going to say n equals 3. So I'm going to do shift by 3, and so I get 0, 0, 1, 2, 3. 0, 1, 0, 0, 0, 0, 0. And so what you see, this is equal to 8, obviously. And then I just -1. And so hopefully you've seen this construct around somewhere, and then I get, 1, 1, 1, 0,
yeah,
0.
Yeah, I remember that one from school.
So this is how you construct these things for n. So basically the construct is remainder equals value and n, sorry, 1, usually unsigned, I think it needs to be, just to make it work properly. Shift by n -1, that. And so this is the thing that you will see, and this is exactly what they put. They've just done the calculation for this and stuck in the result, which is 15 in their side. But this is the magic formula.
Okay, but Oopsie. But I could write it like that, though. I could just say like if I wanted to, right?
Like this.
One,
Oh,
two,
sorry.
shift 16.
No, bit shift 4.
Oh, of course. Yeah.
But yes, minus 1.
Yeah.
And I think you need to have both sets of brackets. Your fancy thing will tell you in short order if any of them are unnecessary, but just because of the way the orders of operations work. Yeah. So
you were right. I needed all of them. Yeah.
So something that might be interesting to do would be to look at, if I can find it quite quickly, let's have a look at Pixel 3D, and let's just do a quick search for okay, well here we go. So here's just some code from River City. I've just done the search for 1U shift.
Nice.
It looks like, well, you would have been over this with your code formatter, so it's probably all like that. Oh, it's not even going to search for, well, still, everywhere you write 1U just about is a bit shift. But you can see here we go, like, this is obviously the bit number, and kind of done it backwards there. Here we go. There's, nope. None of these are exactly, oh, here we go, here's one.
The remaining bits for the input state, yeah.
Yep, so there's that construct sitting in the River City code. I think this is slightly different.
Yeah. What's the mask?
Here's one. So this is getting the remaining bits as masking off 12 bits. So you can construct an arbitrary mask from this. So this is just packing for the GIF writer. This is just selecting. So this is creating this flag as like just writing it out as this. I want bit number 31. Here's another one. So obviously it's a lot of file writing is the only thing. Checks and precision is 17 bits. So it's like I want the bottom 17 bits of this thing, and so on. So that's how you sort of construct masks. Like I want to mask off the bottom set of bits, is you just do that thing, and that's handy to do. But also you can see, you can use it. Like you can stop here and be like, I want the third bit at index 3, so the 4th bit, so base 0. It's like if I shift it to 0, I end up with that 1, 2, 3. And so if I want a specific bit, this is how you construct that as well. If you're doing like bit flags, for example.
Right.
So yes.
Okay.
The only thing to take care of is if you need this to handle, like if say you've got, this is an 8-bit value and you want the whole thing. So if you try and shift 8, it'll go shift, 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 and shift it off the end. Actually, no, that's not true, because then when you subtract 1 from 0, 0, 0, you actually get 1, 1.
Yeah, it'll give you 1 across
the
board.
Why do we? There's a situation that you actually care about that, and I've forgotten what it actually is now. Anyway, so suffice to say you can do that. Oh no, sorry, that's not the situation. The problem is, yeah, I'm like, there's a problem doing that. The problem is
push it off the edge and it's all zeros, and -1 is.
Well, you recall what we talked about the other day, and that is because of the way these things are implemented, you cannot do a shift by 8. If you try and do a shift by 8 on an 8-bit value, it will mask off. It will do its own little mask using this mask here, and you'll get a bit shift by 0. So it'll mask off the 8-bit, which is sitting there. Oh, hang on. It'll mask off the 8-bit, which is like a 1 there, and just give you 0 here. And so it will do a shift by 0, and you'll actually get 0. Does that make sense?
Right. A little bit.
So that's something to be aware of. It's actually written in the spec for C#. So even if the CPU allowed you to do such a ludicrous shift, C# actually specifies that when you do a 32-bit shift, it masks off at 5 bits or whatever 32 bits is. And the same goes for 64-bit shifts. It will actually do the mask if the CPU is not going to do it itself.
Okay.
Just to keep behavior consistent between platforms. Alright, so we're over here. We've selected a position in the tail, and then we've figured out what this is. So this is, yep. So,
yeah, we figured out what the remaining, like what's left, I guess, the remainder of what's left at the end of the tail. And then this is kind of like a sieve, right? Like where it's like, obviously there's only 15 possible values. Like there's only like so many ones, like the 15 ones that we have left. So wherever we enter in here, wherever we start, it looks like it's mixing, it's using XOR, so it's like distributing whatever's left into K2, I guess, because it has nowhere to store it, so I guess it's just trying to distribute it in a hashy way, rather than have to deal with the space that we don't have to fit it. I guess the top part, I gotta say the bottom half is being distributed into K2 and the top part is being distributed into K1.
Okay, so I'm going to stop you there. So there's a bit of a red herring in this code, and I'm very curious as to why they did it this way. I don't quite understand why they did it this way. Possibly, like it may in some weird way be a performance thing. I don't quite know. However, look at what K1 is, or let's say K2, because it does K2 first. Look at what K2 is. It's 0.
Right. Yeah, they're trying to fill it with,
so
I guess one bit at a time.
If it's 0, it's exclusive OR with 0. These are all of them, because you can see where this is going. It's like byte 14 goes into position 48. Is none of these are overlapping, because these are all 8-bit values.
Yeah, so they could have just combined them all.
So they could have done that, and I don't understand why they didn't. So
yeah, what you just wrote there makes a lot more sense.
See,
because they're just copying them into the empty K1 and K2. We're just taking the leftovers and shoving them into new 64-bit blocks, right?
Exactly.
64-bit half blocks.
So I would be inclined to write it like this, just on the basis that it's a little bit more clear what it's doing. And I have no idea why they would have written it as an exclusive OR, unless there's some obscure performance thing that I don't know about.
And is it trying to do some kind of mixing at the same time?
No.
I guess.
Well, okay. So once it gets down to here, it does, and you'll notice that this line of code here is the same as this line of code here.
Right.
And the reason I think that they don't do this line of code is like this actually comes after they've filled K1 and K2 for this one, and it actually mixes H1 into H2.
Is there no more efficient way to take the remaining bits that are left in a well-defined block and just get them and just use them directly instead of copying?
I'm glad you asked. Because that is exactly what I wanted to. I've got a note here. It's like possible discussion. It's like we can talk about this. This is gonna be a great little segue into what I wanted to talk about, and that is why can't we just? Where's the right layer for this? Why can't we just pretend? Like, why can't we just expand out our key, and instead of doing like, can I have the right layer, please? I hate how you can draw on layers that are invisible. It's kind of ridiculous. All right. Why can't I take that and just expand it out to that? And then when I'm done, use some of maybe our newfound powers and just chop that off and just mask that out to 0.
Well, yeah, exactly.
And so why can't we do that? And the reason we can't do that is we don't know where key is, and it may not be aligned. Like if we were aligning it, we could actually think about this in a sensible way. It's a little bit CPU dependent, but you can sort of do that, and then yeah, you could in theory do something like that. However, this could be anywhere. So this, where it stops, oh, actually, sort of, hang on, because these things are relatively huge.
Couldn't we have allocated a whole? Couldn't we have allocated a new place for it to copy the key into?
Well, then we have to do a copy, you see.
Right. All right. Yeah. Exactly.
Otherwise, yes, you could do exactly that.
Right.
So this could be a page boundary, and this could be a page that's been allocated by the CPU as, you know, read, write, and this could be a page that's been allocated as I don't know how you'd write this, not. And so as soon as you touch this memory, access violation.
Right.
So that's why it has to do it this way. So it could be a page boundary is basically the thing. It could quite frankly be like, unless there's some weird reason you can't allocate right up to this. This could be like address, you know, O X F F F da 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 da. And it's like there is no address. It's not even not allocated. It simply doesn't exist. And I guess if you try to do that, it would probably just wrap around and access, you know, OX0000. And we all know what happens when you access that. You also get an access violation, specifically because they always make the first page not allocated, so you explode on a null pointer.
Oh, okay.
So you can, in fact, if you were so inclined, I think, pretty sure you can actually allocate page 0. And then you can access null to your heart's content, but then you fill your program full of bugs because, you know, you're not exploding on a bad pointer.
Although, I mean, what about a working buffer that you pre-allocate and then you leave just for this task? Is that it's still a copy, right? Because you have to copy the key into it, so it doesn't really help.
Yeah. So that is, like, in this case, because we're just reading it, you wouldn't want to do that. However, if you were like writing to the data or maybe doing lots and lots of processing to it or something, that's absolutely something you could do. You could create an aligned buffer. So, you know for a fact that each one of these 64-bit reads is 64-bit aligned. And you could even, once you're aligned, you can use SIMD instructions. And so you could probably do, rather than doing 64 bits at a time, depending on what version of SIMD you were using, you'd do 128 bits at a time, or 256 bits at a time if you've got the name escapes me now, but the later CPUs have larger bits counts for their SIMD instructions. So I believe MMX was 64 bits on its own, and then SSE 2 or something was 128 bits, and then the next one's the next bit count up, and so on. You get the idea. Mm-hmm. So that's a thing that you could do, is you could do SIMD. You can also, if you were so inclined, and it's a little bit tricky if this is not aligned, because you're actually, like, the specification of what the hash is based on this being 0. So you actually have to then figure out, you have to like shift your constants around, so whatever this operation is makes any sense. You probably couldn't do it with this, but some things, what you can do is like, if the alignment is, well, I guess it would be here, if that's the edge of the page. If the alignment is here, you can sort of do this backwards. So rather than doing Well, I guess you'd have to do it at the end as well, maybe, because that's just where I've written the page boundary. So you could pretend that this is, you could pretend that this actually is not this thing, just for fun, and just say the end of that is here. And so what you could do is you could accelerate this section here, because it's got this nice aligned block, and then you have a specialized head and tail that you do in a special way, because you can see this is not a whole thing and this is not a whole thing here.
Right.
But yeah, you can do that. So you clear out this bit, you do this middle section really, really fast, and hopefully you have more than one aligned section in there. So, and then you do the tail, again, using the slow method that can handle it, not being aligned, or not being a complete block.
Right.
So they're sort of your options. But what they've done here is sensible. Any questions about that?
Just case 9 and case 1.
Yeah.
It looks like they're trying to. I guess that's the once they get to so they copy. Say we had all 15 bits, so we copy, and then when we get to 9, that's the end of the K2 block. So then we're doing the mixing, right? That's what this is.
Well, this is why code formatting is important. So the first thing what I suggest is take the first line of case 9 and move it up one line, so you can see what I've got here.
Yeah.
And so this makes it a lot more clear what's happening. It's like,
oh yeah, that's the copy part.
And that's the copy part, and this is the mixing part.
Yeah, distribution of the two constants, followed by, I can't exactly remember the
rotate
reason.
Left 64. Yep.
I guess it's just what they want to do for the algorithm, and then the XOR is the distribution bit thing.
Yes.
Distributing K2 into the hash.
So you're mixing up K2 and then shoving it into the hash. So, and you'll see that this line here is an identical copy of this line here.
Right. Yeah.
So it's still doing exactly the same thing. It's just having to do it on less data. I'm
right.
curious why they didn't do this, and I suspect the reason is just because they're going to call fmix64, which does that sort of thing anyway. So it's probably not that important to do for the tail, to do a mixing step and then just do another mixing step. It's probably a waste of time.
Okay.
So, and there's a weird way you could write this to get rid of, to say if you're exactly aligned, don't do the mixing step in the body either, because you can see that if length is 0, when you take the remainder, if it's aligned, it just skips the whole thing because there is no case 0.
Right.
And so you can envisage, but it will have still just done one of these mixing steps previously.
Yeah, that makes perfect.
So you can envisage a situation where maybe you skip the mixing step if it's aligned, just like this one skips the mixing step, but it's probably, this is such an inexpensive operation, it probably doesn't matter. But it's a neat thing to think about. So,
right. And then the finalizer is doing, I guess, one more mix for luck.
So we're just shoving in the length, which I think this is I feel like this is like a cryptographic sort of thing or something. It feels like someone's just gone, well, we want to avoid a situation where you can sort of generate hash collisions by just shoving in a whole lot of data afterwards.
Oh, is this sort of like a constant time equals type of thing?
No. This is XOR equals. So this is combining in the length with both of the sides of the block.
Oh, I see.
And
okay,
both sides of the hash.
So sticking on arbitrary data and increasing the length isn't actually going to. This is basically protecting against that.
It's protecting against that kind of attack, I think. I'd have to ask whoever designed this, but you can imagine, if I have a string like hello world and someone wants to hash collide with me, they could write a string that's like attack string, and then just like stick on as much of this to get as they wanted to try and get the hash to come back around to be equivalent.
Right.
Although I feel like that just, because then you do a mixing step. I think that's why. So this is sort of outside of my area of expertise because I don't design hash functions.
Right. Okay. But it seems reasonable that that's true. So we'll just.
Well, and that's the thing. You've got this extra bit of data. You may as well just shove it in. Just shove in more data into the hash. It's it's usable.
Right. As long as you're doing it every time, it is what it is. And it's finalization, so it's not a huge. I don't know. I wonder. You wouldn't want to do this because it would be like less work means faster, but whatever. Hash1 plus hash2, so these are being added together.
So
not exactly sure why, because I mean.
Well, you'll notice over here they do it as well, and so it's just making sure that like this, because obviously if you're just doing that and then that and then maybe that and that, then the first 32 bits have no relation to the second 32 bits.
Okay.
And so you actually want to intermingle those things, and so that's what they're doing here and here for that matter.
Right.
And then they just call mix 64, which is just, this is the avalanche sort of stage.
Yeah.
And we discussed that. It's just like making sure that if you modify one bit, it's going to modify lots of other bits.
Right. And I use simulated annealing to find the pretty good, probably not perfect, but good enough distribution constant.
Yes. Well, in fact, they were able to, I think, measure how good it was. It was like 0.025% or something. I don't know what that measures, but it sounds good. It's like, that's a very small percentage. So that's sort of like what the rest of it's
percentage of error or away from them.
I think it might be a percentage away from 50% of the bits, but I mean, I'd have to go and read exactly what it says. I would actually be interested to read the implementation notes on this. I think they actually exist somewhere. Probably should. But hopefully that gives you as much of an idea of how it works as you need to understand it. Certainly as much as I know off the top of my head. So there's one thing that I feel like we should do, and it will become clear. We're gonna do this and stop. So we're gonna leave tail for now again, but hopefully that will make sense because there is a bit of an optimization. But what I'd like to do is I'd like to take the whole thing and make a copy of it that takes a byte array. Hello? Yep, you with me? That's like cursor's not moving and no talking.
Yep.
Yep.
All right, go ahead. I guess I blanked out. I think I may have had a micro nap just now.
Oh, well, we'll finish very soon then, I think. So what I've done is I've copied the whole Murmur hash3 function. So I now have two of them.
Oh, okay.
And I've just changed the key to a byte array. And there's a reason for this. So what you'll find, as we discussed last time, there's never going to be a case where we have an odd number of bytes in the string case. So, we've got 14, 12, 10, 8, 6, and so on in the string case. And so we're probably going to want to do some sort of optimization there to get rid of that. But before we go clobbering up our whole function with optimizations, I think that it makes a lot of sense to have like a known good version of it that is does that make sense? It's like, oh, we need to hash a string, just copy the byte hash and make the modifications we need. Oh, we need to hash an integer, we'll copy the byte case, the known good case, and we'll optimize that version of that. Does that make sense?
Yeah, that makes sense.
So what I want to do here is I just want to go through real quick and not undo so much, but modify our changes for strings so that we're going back to the byte case, and then finish up this tail case so that it compiles as well. So let's just go quickly top to bottom. So obviously, like, length is now key.length because we're not because a byte is 8 bits, not 16.
Okay.
And then we need to modify this. So I'm going to hand this to you. It's going to look very similar, but it's going to be based on 8-byte things rather than 16-byte like chunks.
Oh. Yeah. Okay. So I'll just. Oh, sorry. Having mouse issues there. I think there's something else I got to do, but I'm just doing this part first.
No, this is completely reasonable.
Well, it's still, yeah, this is still 8. So I don't know if it should be I times 8 or I times 4. I feel. Wait, hold on. Why? Okay. No, this is fine at 8, right? Because
No, it should be, well, how many bytes in a block? Because remember, I is measured in blocks.
Yeah. Well, there's.
So it was 8 when we had a string, which was 16-bit items in the string.
Well, block is still 128 bits, so it's still 16 16 bytes. So each K1 should be 8 bytes and K2 should be 8 bytes, I think.
Yep. So and that makes a block. So the total number of bytes in the block is 16. And so all of these 8s should be 16. Are you using a trackpad at the moment?
I have to be, unfortunately.
Yeah, that's okay.
Left my mouse at home.
So what I would encourage you to do is start to get in the habit of doing this thing, the Alt select, just so you can just be like 16. But obviously if you're on a trackpad, I can see how that can be
Yeah,
painful.
I didn't want to. And the plus is got to be. It's not to get to K2. It's the. I feel whatever. I think it's fine the way it is. I guess I got to do the same thing with all these constants now. Rotate by R.
Well, double click on key, and you'll notice key is the only thing that's changed. So we've just changed key, and then once we've loaded it into the 64-bit K1 and K2,
right. That doesn't have to change.
That's fine. So all of this code is fine. So it's just this code. So we're not quite done with this code yet, though. There's problems with it. So see if you can identify the issues.
Well.
So this might be.
I must have to change these.
Sorry?
K1 is still a U long at the end of the day, right?
Yes.
So maybe I shouldn't have changed these shifts positions.
No, those ones are good. However, so what's happened is, and in fact you can see it from which bytes we're accessing. We're going up 16 bytes at a time, but we're only getting 8 bytes out.
It's a little hard to see your screen.
Sorry.
When you say you're only getting 8 bytes, oh.
So see this column here that I've highlighted?
Yeah.
So exactly that. So
Oh.
16, 24, 32, 32, maths 32, 40, 48, hang on, 1, 2, 3, 4, 5, 6, 7.
Did you do an extra one?
Yeah, so
Right one. Yeah.
So this should be the case here, and now I'm just trying to work out what my shifts should be. 0, 8, 16, 24. Although I feel like I've made an error. No, I haven't. That's fine. 16, 24. 50. Maths 56. There we go.
Oh no, my function key changed. Oh, there we go. Fun times on a laptop in a hotel.
Yep.
12, 15,
So you hold up 1 second, because there is an error here. You've gone 7 here, and this is why lining these things up is usually quite important, because it should go 7.
My plus is off the
8,
mark.
Yeah, which means that this should be 9, 10, and so on.
Wow.
And
I don't want to have. I'm missing. Yeah, I'm one more than I obviously should have.
Exactly.
16, 24, 40, 48, 56. Ugh. Hello. Okay.
All right, and that looks correct. That looks good. So now we have like this known good thing, and if like for whatever reason we need to hash something obscure, we could just like cast it to a byte array and shove it in there. It would be nice to be able to use the new feature from C#7, which is span.
Yeah, I love that. And you can just do it in memory without allocating anything.
And then this whole thing would work for arrays or memory or whatever you want. But unfortunately, they were like, you don't need native code. You don't need, well, not native code. You don't need to manipulate pointers. It's like, yeah, we do. It's because, C# is slow in some cases. So let's just come down to tail now. And also length, u-long and integer. So we can I'm just going to cast that to u-long just to make that shut up. Although I'm using u64, so I'll just do that everywhere. So that's just a casting problem.
Oh. Here. Come on, trackpad. I go home. Right.
Okay. So the last.
Oh no, but you're still. Yeah. Okay. You got the unsafe log. I don't. So.
Oh yeah. Okay. So let's get rid of the unsafe now because we actually don't want that. So there's one last thing to do, and that is to fix this line.
Yeah, we need something that we can do an array access against.
So.
Sort of. Or maybe we're gonna get rid of the array access actually. And just use a bit shift or whatever.
Well, let's have a little think about where we're at. Like what is this doing? It's like it's taking key and it's seeking n blocks times 16 into key and telling us what tail is. So if you think about it, tail, like you could do this, for example, and so on.
Right.
So we could do the same thing by hand. So does it make sense what we're going for when we do that?
I mean, yeah, because you're kind of just redefining the pointer every time you need it, as opposed to like doing it in an unsafe way. Here, is that what you mean?
Well, what we need, like, we have to get rid of tail because tail is a byte pointer.
Yeah.
So and again, if we had span, I believe you could just say, all right, well, give me the span that is what is it? A slice. You just call slice on it and pull off the end of it and get tail that way.
Yeah, that's right.
But because we're stuck with this, we have to do something that basically turns, like, we can't create a new tail. We have to always use key. So this is going to be key, and this is going to be key, and whatever we stick in here is going to do the equivalent of this.
Right. Yeah, but I just don't know how to replace it because this is obviously not the 14th access. Like, it's not trying to index that character in the key. Byte in the key, right? Yeah.
Correct. So we're not going for byte 14 in the key, but we're going for byte 14 in the key plus this thing. So it's like the 14th byte after all of the 16 byte blocks that we processed up here.
Right.
And so what we might do is just to
R that out.
just pull that out just to make the compiler's job a little bit easier.
Excuse me.
And that sort of ties into a thing that you learn, like when you're working with pointers, and it applies in both C++ and C# when you're working with pointers, is let's say byte star foo, or even like int star foo, like, because this works based on the pointer size. So if we have foo index 12, this is equivalent to writing this is equivalent to writing foo plus 12 and dereferencing it. So does that make sense how these two lines are equivalent?
Yes.
Good. So when you do when you want to advance by some number of 4-byte elements, it's the same as indexing to the 4-byte element. So pointer addition is always based on the width of the pointer. So this is not 12 bytes, but 12 times 4 bytes.
Yeah, I feel it. Yeah, I should have got that.
No, that's all right.
Great. Here. But yeah, this makes a lot of sense. Although there's still a compiler error somewhere.
Is there? We'll
Maybe just
try and fix that up.
Oh no, it's just a stupid thing complaining that there's no default switch case, but we don't need one.
Yes, exactly. So
that's redundant, but I'm gonna put it in anyway.
You could, like, yeah.
I think I've got it set to like compile errors as warnings as errors or something. So anyway, now we're good.
Okay, and so yeah, there's this week. I can't remember what it is now. It's something like this is also equivalent in C equals. Is it 12 foo? something bizarre, like you can do like that kind of nonsense or something like that in C and it actually works. Something like that is really peculiar. I can't remember the exact details, but there is a bizarre thing I should find. Okay, so I think that's where we'll wrap up today. So we should have, in theory, there should be no errors in this one. And what we can then do is like, all right, we'll take our known good one and we'll probably copy this section into here, and then we'll go through and modify this to be exactly the same for string. Sorry, exactly working for string. Then we can just copy the whole string one. So just copy, change it to string. Although don't do this now because we're gonna undo it in a sec. But like we'll be able to do that, and it will be identical code. And then we can also do it like just copy paste and then like int.
Yeah, I just copied tail and the finalizer into the string one to make it work, or compile, I mean.
Okay. Certainly stick a massive to do. I will do the same, but we're gonna have to go in and modify it because obviously key is different.
Oh right, it's not. Yeah, it's. I got to go back down to the string version of it.
I mean, how are you feeling? Do you want to wrap up? We're a little over time. We could do this now.
I think we can. We'll have to review it anyway, so we'll maybe just pick it up next time.
Okay, so I'm just gonna do bug make this work with car. So.
Right, that makes sense.
Because obviously all of this indexing is wrong.
Or because it's on a 16-bit character, not an 8-byte.
So it needs to match this thing we've done, this I times 8 plus blah, whereas this is like I times 16 plus blah, and obviously,
right.
Yeah, you can see how that's a problem. So we'll go through and make that change later. All right, thanks for watching, everyone, and we are